Test, test. Welcome. Do you hear me? Welcome to this afternoon of the SFSCon 2021. It's the software architects track, and this year the conference is blended, so glad to see some people here. So this track has 11 talks. We are going on till 6 o'clock in the afternoon. Each of these talks will have a duration of 15 minutes, including question and answers. You could do the questions, of course, with a microphone. We have a microphone here if you are in presence, and if you're watching us online, you can just write below the video in the chat. Keep in mind that there is a delay for about 1 minute, 1.5 minutes. So if you have questions for a speaker, make sure you write your questions way before the talk ends, so that we have the time to read them and to forward it to the speaker. Questions made offline, meaning here in the room, have precedence, so we handle before them and afterwards the others coming from online. All right, so our first speaker is Sander van Doren from the European Commission's Directorate General for Informatics. And he's talking about JoinUp, so to how to maintain an open catalog of reusable solutions with linked data. So welcome, Sander.
Hello, thank you. Well, it's a pleasure to speak at this conference, and I'll since we have a very limited time, I'll dive right in. So as was just mentioned, I work for the European Commission. Although I don't work for the European Commission, I'm an independent consultant working for the European Commission. So don't ask me political questions afterwards, since I won't be able to answer them. But okay, so the last few years I've been involved in this project called JoinUp at the unit for interoperability at the European Commission. And this unit within the European Commission is really about promoting, well, being able to exchange data across border. And for this, a lot of things need to work together. And one of the ways that that we hope we can, be able to work better cross border is by promoting open source software to the member states of the union. So one way that this happens is through the JoinUp platform, and because the JoinUp platform is, in fact, it tries to be a comprehensive catalog of solutions that exist, that are created in the member states, that can then be reused in other places. So it's an open catalog of reusable solutions, and reusable solutions can be things like free software, but it could also be things like standards, for instance, since they also promote interoperability. So very quickly, I think I already touched upon a few of these things. JoinUp tries to be a collaborative platform. So the goal is that people can really work together on the solutions that they create. But it's also at the same time a bit of a policy place where, you know, things people can be informed about changes in for instance, open source policy of the union, or studies around things. I mean, it's a bit of both. And of course, there is the collaborative aspect, but mainly it is a place where people can go and discover these solutions. So there is this aspect of being really a catalog of these things. So I arrived on this project a few years ago, and the project was already ongoing, and it was built in Drupal 6. So the at that time, Drupal 8 was about to be released, and Drupal is an open source content management system. If you're, for those who are not in this realm. And what was asked of me was, okay, we need to sort of rethink this platform, since the previous version had quite a bit of issues being able to exchange those solutions, because of course there is this European platform, but of course all of these member states of the union can already have their, I mean, maybe not all of them, but some at least have their own catalogs of reusable solutions that can be used, for instance, across regions, and that are being developed by one administration, and it can be reused in other parts. So these catalogs already exist, and the previous version had big issues in being able to pull in the data from these other catalogs, member state catalogs, and there we needed to find a solution for this. And since, well, we're promoting open source, the whole project was also built on open source, and so everything that we do for the JoinUp project is also open source on its own. So that's quickly a bit of a representation of the JoinUp platform. On the other side, we, I mean, what is really the focus of this talk is the linked data aspect. So very quickly, linked data is a way to represent information. It's a way to be able to exchange information in a standardized way. It was standardized by the W3C, so it's really a web specification. And for those of you who are around for a while, in the early 2000s, you had this big movement of the semantic web, and this is really what this is all about. Only now, in the last few years, a lot of things have happened, and it's actually more and more being used by public administrations. So the way that linked data represent information is this very atomic triple. So one piece of information is represented as a triple, and you can really see this as you have at one hand an entity. An entity has a field or an attribute, right? And then that attribute has a certain value, and that's really all there is to a triple. And you know, it's this atomic statement about the being of an entity, sort of. So and then of course, if you have this linked data, it's a graph structure. You need to be able to store this one way or another, and this we do in what we call a triple store. And triple stores are a type of database, a graph database that you can query in a specific, also standardized query language called Sparkle. So why did we decide to use linked data? Well, since we have all these catalogs also maintained in the member states, what we decided to do is to model, and this is how I arrive at my next slide. We decided to make a data model that is, well, it's agreed upon by the member states of the union, called ADM SAP, and that really describes all of the metadata of how to describe these reusable solutions. So a solution has a publication date, it has a way of categorizing it. I mean, you can imagine that well, there is a lot of things to be said about these things, about solutions. And in order to be able to exchange between these multiple catalogs, we needed a unified way. And instead of developing a standardized API contract, which could have been one way of doing it, we only standardized the data model, but we decided to go with linked data, and that way we also have an easy way of exchanging data. Maybe later on I can get a bit more in detail on the advantages of using this approach, but let's see on the time. So in the end, we had conceptually we agreed that that we needed this linked data to exchange information between these catalogs. But of course, we had our CMS, which the Drupal CMS did not have any notion of Sparkle or this graph thing that is behind. And so we had to develop everything from scratch to integrate those two worlds, let's say. And that way we arrived to develop an integration, a plugin for Drupal CMS to talk to a Sparkle endpoint in the backend. So to be able to integrate a triple store database with our content management system. And of course, well, this has some advantages and some disadvantages. You could say that a disadvantage is that, well, you have to support a whole technology stack, a whole database driver on your own, which is not a trivial thing to do. But what we discovered from the previous version of the platform was that where we also had support for this linked data in order to be exchanged between those catalogs. There we had exporters and importers mapping the internal data model of the application towards the exchange data model, which was then this ADM SAP specification. So we always had these data conversions in between. Well, now with our database driver, we can remain in the standardized data model within our application, and we can really take on the whole agreed upon domain model into the heart of the application. And we have this nice separation of the layers of our model. So we really have a business layer and all the technical, the mapping to this data model. I mean, the orchestration. I mean, how to actually write Sparkle queries. That's in the database driver, and you don't need to reason with it while doing actual creating business logic in the application. Another things for people who know a bit of linked data and perhaps a bit of Drupal. Another thing we really desperately needed was a way to map Drupal taxonomies to SCOS taxonomies and SCOS is a way of representing taxonomies in linked data. So when you have a taxonomy, for instance, food types could be one taxonomy, and you could have vegetables and fruit as two terms in the taxonomy. Well, you want to be able to tag content with this. Drupal uses taxonomies for this, and in the linked data world, it has an equivalent. So we also had to bridge those two worlds, and for this we had to create another little piece of open source software. And then for integrating with these third-party catalogs, well, we needed sort of a batch ingestion engine to bulk load and validate the data coming from those catalogs, because of course you cannot always 100% trust the conformance to the schema that you agreed upon by those third parties. One catch in all of this was that in our content management system, we could not model everything in using linked data. Because one reason why is that in linked data, well, now that we have enough confidence in our technology, it would be fine. but doing things like versioning was very difficult in our first iterations of the database driver. So that's why we still store some types of content in a normal relational database. But then we ended up, of course, with a different problem that was, okay, now we have two database backends behind this content management system. How do we query this if we need to retrieve information that resides in both of those engines? We need to be able to query across two databases using completely different technology. In the end, the solution that we came up with was to use an Apache Solr. So we query our search engine. We ingest everything of those two backends into Solr. The queries go to the Solr instance, and then this Solr instance returns entity IDs. We load the entities from the really system of record databases, and then yeah, we can render them on screen.
Sander,
yeah, I see we're tight on time, but if I didn't run out of time, I would have had a short demo here. But I think we can wrap up here and move to the questions then.
Well, the question time would have been included. So
okay. I'm sorry.
For, changing rooms and so.
Okay, perfect.
If you want to, can say some final words to wrap up.
No, it's if people are interested in this kind of linked data and combination with content management systems, feel free to reach out. The contact points are all in the PDF that I hope will also be made available, and then you can feel free to reach out and get in contact. Yeah, also sure. For questions, I'll be available there.
We will upload all presentations to the website, and as well all the videos are recorded, so it's viewable afterwards on YouTube. Okay, so Sander, thank you very much for having you here, and we move on then with 3.5 minutes pause, and then the next talk. Thank you.
Bye.
right, welcome back. Track 2, track 1, software architects of the SFSCon 2021. We have our next speaker here in presence. It's Daniel Frisingelli. He's a researcher at the URAC Research in Bolzano. And he will talk about the cost of traditional machine learning and the deep learning models on Earth observation. And he will present as a case study, right? So the comparison between accuracy and the cost of deep learning algorithms.
Yes. Thank you very much for introducing me. So I thought of starting this presentation with a, let's say, short introduction on which data we are using in Earth observation, since I know that there are people from very different backgrounds in this conference. So let's get right to it. So what is Earth observation data? And it's basically multispectral images collected by satellites which measure the radiation reflected or emitted by the Earth's surface. And they do this in different parts of the electromagnetic spectrum. And they do this also continuously, so they continuously acquire data such that we can observe changes of the Earth's surface through time. Now, as you can imagine, there are a lot of different satellites out there that measure different properties of the Earth's surface and also of the atmosphere. And this leads to an ever-growing amount of data that can no longer be easily processed on a standard desktop or also laptop computer. So therefore, we require powerful cloud-based systems and platforms which can provide, first of all, access to the data and also provide powerful computing resources to process the data. And in this context, we are currently working on a project at URAC Research, which is funded in this case by Microsoft and the group on Earth observations, where we were granted access to the Microsoft Azure cloud platform. And the goal of this project is to integrate data from different sources, in this case terrain, climate, and land cover information, to derive a high-resolution map of mountain ecosystem extent. And today here I will talk about our machine learning use case within this project, which is about high-resolution land cover classification. So let's get to the problem. The classification problem we are dealing with is a supervised machine learning problem and therefore requires a labeled data set. And the labeled data set basically consists of the input data, which in our case are the satellite data, and of the corresponding labels, which are the land cover classes we want to map. So if we look at the example here shown on the slide for the province of South Tyrol, we want to train a machine learning algorithm that, given a satellite image, assigns a land cover class to each pixel in the image. Now we do this using an open data set, which is called the Harmonized Landsat 8 and Sentinel-2 data set, and consists of a time series of images from the Landsat 8 and Sentinel-2 satellites. All the images have a spatial resolution of 30 meters per pixel, and they are structured in tiles of a size of 110 kilometers square. And this results in, let's say, a physical image size of around 300 megabytes per image. And since these images are acquired at a regular frequency of 2 to 3 days, this amounts to approximately 200 images per tile in the year, which, for instance, for our small province of South Tyrol only, these two satellites acquire around 250 gigabytes of image data yearly. So this is quite a lot of data to handle. So as I explained one slide ago, so we also, alongside the input data, need corresponding labels to train the machine learning algorithms, and collecting labels in the field of, let's say, land cover classification is usually done manually. So you can think about an experienced analyst who is using GIS software to label exact locations, which are then used as the training data for the machine learning algorithms. And this is obviously a very expensive task, and in our case was not feasible, since we were trying to classify land cover for large areas. And therefore we implemented a different approach. So we implemented an algorithm that basically tries to extract the labels for the classification tasks from an existing land cover product. And here we're using, for instance, the European Korean land cover. And if we look at the figure here in the slide, it shows you the land cover of the city of Bolzano and its surroundings as represented in this European data set. And the goal of our algorithm is to extract the most representative locations for each land cover class from this layer. And these locations will then be used to train the algorithms to extrapolate to different areas. Now, our algorithm consists of multiple steps. And the first step is basically that we remove any pixels that are located on class boundaries. And this means that we are able to basically decrease the likelihood that you use pixels which have mixed information from different land cover classes. And as you see in this resulting map, this step removes quite a lot of pixels from the original product. And then in a second step, we combine the satellite data with statistical methods to detect further outliers within each class. And so, for instance, if you look at the zoomed inset view on the lower right, you see an orchard northwest of Bolzano, and which is entirely labeled as orchard in the European product. And after the outlier removal, you are able to remove, in this case, the river and some buildings from the orchard, which were wrongly labeled by the original product. And so we use this finally filtered product to extract our training data for training the algorithms, and then in a final step combine this with the input satellite data to run the classification. So speaking of algorithms, we have implemented and tested two different algorithms for this task. The first one is a random forest-based algorithm, and also a more complex deep learning approach, the convolutional neural network. And so the random forest is, let's say, a more traditional machine learning algorithm, which is based on an ensemble of decision trees, and it requires more careful selection of the input data. And on the other hand, we have the convolutional network, which is a deep learning approach and is more complex and also more flexible. And it can directly work with the time series of the satellite data. And both models are probabilistic, such that they give you the probability for each class. So to sum up all the concepts I have introduced, here is a short workflow. So we start with the land cover product and the satellite data. We run our automatic label extraction algorithm to get the training data. And then in the classification step, we combine the satellite data in addition with a DEM model to train the algorithms, and then finally to produce the final land cover maps. And let's say this whole workflow is implemented in Python 3, and it is open source. And the development of it was quite an iterative process, which I will try to explain with this figure. So you start with an initial prototype, which is, as I said, written in Python 3. You deploy the data and the algorithms on very powerful virtual machines in Microsoft Azure. You produce the land cover maps, and then after producing them, we visually check them in our team, and then also implemented further improvements and also modifications to the workflow, and this then closed the iteration. And basically here I want to say that to arrive at the current state of our algorithms and the resulting maps, it was quite a lot of iterations of this process were necessary. So enough of the methodology. So here is an example of one of the produced land cover maps for the province of South Tyrol. It has a spatial resolution of 30 meters, and it represents 11 land cover classes. And let's say the classification of this map was based on data from 4 tiles, And if we use images with a cloud coverage of less than 50%, this was about 40 to 80 images per tile. And this translates, let's say, to around 50 to 100 gigabytes of input data for the classification. And let's say the computation time to produce this map is around 2 hours for both our models. And for the particular virtual machines we were using in Microsoft Azure, this translated to a cost of around $6.50 to $7 to produce this map. Now, after we have observed the performance of the models on this relatively small area, we were interested on how the approach scales to larger areas, and therefore we applied it to the area of the European Alps. And let's say the resulting map, which is shown here, is again at the same spatial resolution of 30 meters. But the amount of data that you have to process to generate this map is a factor of 10 higher. So in this case, 500 gigabytes to 1 terabyte of input satellite data were necessary to produce this map. And the computation time is on the order of 1 day for both models. And the cost is around $70 to $80. So I think we can say that we have quite an efficient workflow in terms of both computation time and also the associated cost. And finally, here I want to stress that we are still in the first phase of this project, which means these are the first preliminary results that I have shown here today. And these maps still require validation, so a proper accuracy assessment. And our first estimate of the accuracy is around 70%, which is also comparable to other currently existing products. And yeah, finally, I want to also highlight that, let's say, validation of land cover is quite a hot topic in Earth observation, and it's limited by the fact that there is no true reference ground truth data that you can use to validate the maps that you have produced. So yeah, this is it from my side, and yeah, let's say if you want to know more about this project, here is the link to our website, and of course also you can scan the QR codes to check out all the algorithms that we've developed. Thanks, thank you very much.
Thank you very much for this talk. We have about 2 minutes for questions. Are there any questions from the audience? Can you come out here to the microphone? Thank you.
Yeah, thank you, Daniel. Curiosity, actually. Did you sort out already how is the improvement that comes when you do this step of outlier detection and removal? So you said that you got to a correlation about 70%, basically, I guess, including the fact that you already take apart the outliers. But what if you don't do that step?
Well, let's say it depends on the resolution of the input land cover product you use to collect your training data. The better the input product is, the better the let's say, automatic extraction algorithm works. And so in summary, I would say that it is very likely that you have a low resolution product, around 300, 500 meters resolution, that there are a lot of pixels included that are not associated to the correct land cover class. And if you don't have an outlier removal or something in place, these pixels will get wrongly included in training your algorithms, and this can then cause substantial, let's say, problems in the classification.
May I add another part of question? Now it comes to the difficult part. Because actually, you know, I'm the one who should give you something from the ground in situ, no? So when it comes to sensors. So do you have some idea which could be the sources of these outlier events? Because if we know that, then maybe reinforcing our sensing on the ground, looking at particular events, can really help you to get rid of all these let's say, unfavorable data. But if we know which could be the source, the physical source, would be much, much better. You do have some idea about that, why these outliers occur? Is just some problems coming from the processing, or there is some physical, I don't know, I'm thinking about clouds or whatever.
I think there are a couple of problems that you can face in this, let's say, whole workflow. But the main issue is that the definition of the land cover classes can very much differ depending on the product that you use. So let's say a cropland is not a, let's say, does not include all the different crops that it does in one product, and in another product it includes other classes. So there is also, let's say, the issue of the definition of the classes that you use.
Thank you.
Right. Thank you very much.
Well, thanks. Thank you very much.
Thank you, Daniel. So, okay. Thank you very much. Now it's time to move on for if you want to change room or stay here. In about 4 minutes, we have the next talk. Thank you very much. right, welcome back to the software track. Now we have the next speaker. His name is Mohamed Sadak. He's a data scientist at OnTopic, which is a spin-off from the University of Bolzano. And he will talk about the open tools for crafting natural language. So the presentation of all required tools for an end-to-end project in artificial intelligence and machine learning. Is that correct?
Thank you. You hear me well? That's good. Okay, as the introduction, my name is Simon, data scientist at OnTopic, and we work on a variety of NLP projects, starting from semantic similarity, search engine, information extraction, and much more. And in the process of going through the lifetime of each project, we observed some best practices, some ideas, and also some needs that needs to be tackled. There are needs for NLP and VKG users, and we want to package them in an open source way, because OnTopic actually believe deeply in the open source. So I will start by this case, this recent project we are working on. It's information extraction from regulatory code. So information extraction is extraction structured data from unstructured data, which is text. So basically we want to transform this article into a more structured way, so to automate the compliance validity, or like to validate automatically the compliance of building code. So, and during these projects, we face these challenges. Which NLP task is related to our project? Which tools need to be worked with? Evaluation, what metric we should use? Tackling the training data problem. It's scarce, it's expensive to have, and the methodology on how to go through the project in a way that accelerates achieving the goal, and also what tools that will help going more productive and fast in the development. And lastly, how to integrate this component into information systems. This topic will be about these bullets, so stick around. We start by notes for development, as we saw that normally you are a coder and you should use software engineering principle, solid principle, single responsibility principle, open for extension, closed for modification, and much more. I won't go to the details about this. You can actually borrow some chapters from this book. It's really good. And a second, Jupyter Notebook, it's more of demoing and teaching code, and it's really a mess. You need to deal with tracking order of cells because of the caching. You need to solve the problem of version control. If you want to review a PR or to merge, it's really hard. It's really a mess. And if you want to solve this one by having like a tool, I would say why, because you will need to rewrite and refactor your code. Also, use experiment tracker. Don't rely on your memory because you will forget. Paper, you will lose it probably. And any kind of sheets, you already have a lot of sheets, so just use experiment tracker. And from all the software that is there, we want something that won't hijack your code, will provide all the features you want. And there is MLflow, there is Scare, there is a bunch of others. We picked Guild AI because of these reasons. It's easy. It's snapshot your source code, as not any experiment deserve a commit. It's super powered by hyperparameter tuning, by remote training, and much more. You don't need to write the Guild AI code into your code, so it stays clean. No databases needed or any exotic file system. On topic, we use PyTorch, and after we figure out the model that will serve well, we want something that will give good prediction, good time and speed. And PyTorch provides TorchScript, which is a serializable way of converting the model, and it runs into just-in-time compiler, and it's really easy to use. You can use it with Python by two functions, trace and script, and the difference between those, you can check them in the documentation. The trace doesn't follow the code flow, so if you have any if statement, it won't catch it. On the other hand, script is it will analyze the source code and catch these if statements, and if you have any code flow. And also, yeah, so to skip the limitation of GEL in Python, you may consider a multi-threading environment, which is the best one, which is C++. It's easy to use in C++ too. So after converting the model in Python and saving it, you can load it from C++ very easily. For the API and to serve the model, first we were using Flask, but as we were limited by the I/O limitation, we switched to Fast API, and hence the name. It's fast, it's asynchronous, and built-in Swagger for free is there, and which is cool. Dealing with complex checks. Given the project we saw previously, we deal with checks that is complex. That is like this, with low readability score, with complex texture, and even the most the arch of the stage models can't perform well on these kind of sentences. So only if we can have this sentence transformed or like deconstructed into more simple sentences like this. And it turns out that there is a task for this. It's called check simplification, which is different from check summarization. It keeps all the information. It changes low readable words and reconstructs complex phrases. Consider this example from Turk dataset. It converts this sentence into more like this. It turns out that check simplification improves many tasks: machine translation, information checks, information extraction, and it serves in prediction time as a middle between complex phrase and the model, or in training time where you need to augment your data. However, there is no one approach that can solve all the problems. So, the experiment or like the experimentation of each approach to see if it will serve, it will be the right one for you. It's really complex, as you need to go into the complexity of each approach and its particularities. So only if we could have something with wraps all the main SOTA approach. SOTA stands for state of the art. Brings everything to Python, because there is some approaches in other languages, and hide all the complexity. Simple to use, just call a function and turn a complex sentence into simple sentence. Actually, Simplify comes to the rescue. We started this project by providing all the SOTA models to be available, and you can check it now. You can also feel free to contribute if you want. Yeah, and after we finished the modeling and everything, NLP services, they are more one entity of a large system. So we have applications that interact with the data source, and there is two common ways to exploit the NLP services. Is one, offline manner, by having all the data through the NLP and store the prediction, and then the application would access the results. The second fashion is the online one. So you have the application that will directly invoke NLP service and serve that result to the end user. However, for this architecture, we have two main issues. One is the data access. We want, for a case, we want the application to access both the data sources and NLP services, and it really gets complex when your data sources is more heterogeneous. Consider files and database and much more. And also the orchestrate of process and materialization are tracking the changes in data sources, as in each one, in each change, you need to rerun the process or the prediction over all the data you have, which is expensive. For these problems, they can be solved by many ways, and because that's on topic, we deal with VKG. VKG, knowledge graph, you may already know, it stands for knowledge, for representing data and information into more a graph-based. You already know the Google knowledge graph, which is the sidebar of each query that presents you entities that are relevant to your search. And virtual stands for, and virtual VKG means knowledge graph that are visual. It doesn't require to be stored on any database or triple store. It just invoke a view from a relational database, for example. And the idea is we want the VKG to embrace both data sources and NLP services. So for the moment, we already have the first support that on top supports data sources, and you can download it from the website that will be listed in the end. And the extension that we are working on, it's Hive, which will support the tracking and orchestration, and also the online manner of invoking these and merging both results. Hive is a project that is a collaboration between Noi Tech Park on topic and Unibiz, funded by Sparkas. Yeah, so this is the end. Thank you.
Okay, thank you very much. We have 1 minute left. Are there any questions? No questions so far? Okay.
It was more complex.
Thank you again.
Yeah, thank you very much
so we
for
can stop
attending.
here. All right, welcome back to the Software Architects track of the SFSCon. Now, next speaker is Gary Skendry. He's a PhD student at the University of Verona, and he will talk about the transformer revolution and attention-based machine learning. So, how to use open source to reproduce models of transformer neural network, where the question is attention really all you need? So, welcome, Gary.
Hey everyone. So I hope you can all hear me. Unfortunately, I couldn't make it there in person this year because of some deadline issues. But anyways, my name is Gary Skenderi. As it was already presented, I'm here to talk about transformers today and attention-based machine learning. I'm actually glad we had an NLP talk before, so you're not just strangers to the topics. So anyways, the talk is going to be a short introduction to this problem that many models have when modeling sequences and why attention is needed, transformers, and then we're going to see some variations and applications and where you can find some open source code to start playing with these models. So let's get into it. Now, first of all, if you're wondering, we're not going to talk about these transformers today. Although they are cool, we're talking about machine learning and specifically deep learning, which is a subfield of machine learning that has to do with representation learning itself. So we learn meaningful features directly from the data, right? We don't need to do any other pre-processing or like feature engineering. Now, this talk does require some familiarity with, machine learning and like deep learning architectures in general. You don't need to be an expert, but it does require some sort of, let's say, not knowledge, but experience. So there is this particular problem in learning tasks, which is called sequence to sequence. So this is essentially dealing with the problem where we have a sequence, say, for example, in translation, we have a sequence, which is a phrase, right? So a phrase is a sequence, it has an order, and then we need to transform this to another sequence. Now you can see here the phrase, she is eating a green apple, which has to be translated into Japanese. And so, of course, when you do this automatically, you need to learn how each token maps, to the other tokens and understand how to actually perform the translation. Now, there's some issues with these tasks. The first is, some words, especially in sentences, have much more or they have a higher importance, let's say, for some other words, like say eating, for example, an apple. So when you read the sentence and you say and you see she is eating, you immediately think of, okay, what is the food? So I don't care about a or green or is. The other thing is that when you work with these structures, you create a context vector, which is essentially a vector of numbers that tells you what each token maps to numerically. What happens when the sentence is very long? So say this vector here is 5, but what happens if it's n, right? So what happens for very long sequences? Typical neural networks that solve these problems, like LSTMs or RNNs, they suffer from these issues, which are called limited memory. So that's basically having a limited amount of memory regarding the context vector. So after a certain while, you start to forget what happened before. All the tokens have the same importance. So going back here, you see that all of the words have the same weight, essentially, for the other words. And the problem is training efficiency. So here you have a sequential problem, right? So if you just go step by step by step by step, if you have very long sentences, this can get very inefficient. And so this is why Google presented in 2017 with a very famous paper, which is called Attention is All You Need, this transformer architecture, which is what you see on the right. So now it looks very complex, but it's super simple. Essentially, this is just a feed-forward neural network with multiple layers. What makes it different is this multi-head attention that you see here. And that's what we're going to talk about shortly. So essentially the title of the paper, as I mentioned before, is Attention is All You Need. And the authors argue that for NLP or sequence tasks, all you need is this attention mechanism to learn dependencies. You don't need anything else. As you can see here, the network works in an encoder-decoder way. So you have on the left side, you have an encoder, which takes a sequence, right? So think about the English sequence before. Then this encoder creates a representation of the sequence, which it feeds to the decoder that on its own right has gotten a sequence. So for translation, this is a sequence of, tokens. So it's just a token that says basically translate the sequence before. And then what happens is you process using attention, and then you just create, you just find a distribution over which is the most likely word that comes in that place, right? So how does this attention thing work? Okay, so now we're going to get a bit math savvy here. It's not going to be anything too complex, but you're going to need to have just a tiny bit of familiarity with dot products, essentially. So what they propose in the paper is this scaled dot product attention, which means basically that they try to find, how similar some representations are in space. So I'll try to explain that as practically as I can. So the input to an attention block is divided into 3 parts, and this is information retrieval terminology, if any of you are familiar. So you have a query, you have a key, and you have a value. And what you want to do is find out how similar the query and the key are, and then use that similarity to multiply the value. So essentially, if you had, think about the sentences before, you try to find out how similar, or by similar I mean like in a a vectorial sense, not similar as in word per word, for example, or anything like that. So you try to find out how similar these two representations are, and then that gives you a weight, and then you use that weight to multiply the values. So what this means is I'm trying to find out how important this query is to the value. Okay. The way we do that with attention is that we first take our input. So this is a description of self-attention here, right? So you see that the input is X, the green blocks. The input is just replicated 3 times, and then it's multiplied by a weight matrix. So this is a linear transformation. And we get this query, we get this key, and we get this value. So now we have these 3. All we do is we just apply a dot product, which again gives us the similarity. And then we scale. So you see we divide this by the square root of dk. So dk is just the dimensionality of the model. And actually this division is just done for numerical reasons. So it's there just for show, basically. You don't really need it, but it's for, like gradient descent. We won't get into that. So then you do a softmax, which just means that you normalize these values so that they sum up to 1, right? So this gives you a probability distribution. And then you multiply this by v. So all you're doing is essentially creating a weighted mean of the value based on the query, right? So the reason this is important is because this attention, this dot product, you can apply it for any size. Of course, virtually any size, given that you have enough processing power, but you can do this for any context vector and any long sequence, and you will get a weight for each word. So this basically creates a very big advantage, because you don't just have the ability to process very long sequences, you also can remember infinitely long sequences, given that you have infinite processing powers. So now let's see some applications with some code for any one of you who is more practical. I know this part was a bit theoretical, so yeah. So first of all, we'll look at vision transformers. So now these are just the feature extraction models used for computer vision. If any of you worked with images before, you'll know convolutional neural networks. And so these are just a variation of transformers which are used as CNNs, basically. So they are developed by Google as well. All that they do is basically they take an image and they divide it into parts, and then they just create a sequence of these parts. So they say, okay, so this is the top left, and that's part 0, and part 1, and part 2, and so on and so forth. And they feed this into a transformer as if it were a sequence of words or a sequence of symbols. And this gives you a probability distribution to learn what the image is. And you can find the code. I'm linking the code and the papers in the end of the slides for all of these variations. So you can have it, you can easily find the code in GitHub and play with it. Another very nice application of transformers is DALL-E. So this is a text-to-image generative model. So it basically creates new images given text, and it processes very multimodal data. I won't get into details, but what essentially they do is they learn some characteristics of images and also some characteristics of text. And what they do is they merge these together and feed them into a transformer. So they're using it to model bivariate distribution. And it's very nice. You can see in the examples that they managed to create absurd images here. A very nice application as well, if I do say so myself, is GTM transformer. So this is actually a generative forecasting model. It doesn't have decoder self-attention, so it's a modified version of the architecture. And it allows you to forecast or to predict time series which don't have a past. Now, this was developed by our lab here at the University of Verona. And it's very nice because essentially, imagine you have new fashion products coming out next year. They don't have a story, and you can model such problems even if you don't have that historical past, which is a very limiting factor sometimes. We also made the dataset available actually for this approach if any of you is interested, because it's the first in its task, and we really do believe actually that open access to data is sometimes even more important than code, because code can be replicated, but it's very hard actually to work without data, especially in of course data analysis tasks or machine learning, because the quality and the openness of data is one of the biggest limitations when it comes to breakthrough research applied in the industry. Here you can see how GTM works. So you can see the improvements, especially in the first row, with other competitive approaches, which I won't be getting deep into because, of course, that's not really the topic of this presentation. But if any of you are interested, of course, you can send me an email or have a chat with me. And if you're interested in forecasting, you can try it out. It works really well, and it's very scalable as well. So the conclusions are, of course, these models are not the answer to everything. So, it's not like you have a problem and you take a transformer model and you use it, because that's not, of course, the solution. They work very well for sequence to sequence, not just because they can learn so many things, but because they can capture complex dependencies, and they also are very interpretable. So if you see the attention weights, you can understand which part of the sequence is the most important. They are hard to train and understand in the beginning, so they look very complex, but of course, as anything else with experience, you get much better at it. And a lot of code and libraries are available as open source. In this slide, I've shared my favorite one, which is Hugging Face. They have an amazing API full of transformers that you can use like out of the box. And you should try it out and play with it, and also with the approaches and applications I presented in this talk. So thank you very much. I just want to say that I'm deeply indebted to Lilian Wang and Jay Alamar and their blogs for the pictures I've used in this presentation. So thank you all.
Thank you very much, Gary. Very impressive. Are there any questions from the audience? No questions so far? Okay, so thank you again, Gary. We will stop here and then see us at the next track in about 6-7 minutes. Thank you.
Perfect.
Speaker is Justina Ivanova. She's a PhD student at the Free University of Bolzano. And now we are talking about sports, so recommendations for climbers. And there is a source example between direct feedback and sensors, so a combination for their prediction of their behavior. So, word to you.
Thank you very much. Hello, everyone. As been stated, I'm Ivanova Justina, current PhD student in Free University of Bolzano, and today I present climbing recommender system. This is the content of the presentation. First, I will introduce you to sport climbing. Then I will present recommendations for climbers. After that, I will talk about activity recognition and how it can be connected with recommendations. Then I will discuss related work and outline design proposal for climbing recommendation. After that, I will present free software employed for the project and introduce future plans. Let's start with the introduction to sport climbing. Sport climbing becomes very popular each year, and this is the statistics. We can see that total US climbing gyms increases every year, and US climbing gym growth rate is positive since the beginning of the century. Climbers are interested to climb in different places around the world, and unfortunately, there is a lack of an electronic support for climbers. Electronic climbing guidebooks do not include any suggestions yet. And we came up with this problem. We would like to create recommendations for climbers, where we would like to create an innovative and useful decision support tools for climbers and gym owners. we would like to automatically detect climbing activities because it's important for this step, and to understand what climbers are doing at the certain time point is an important step for modeling behavior of climbers and for supporting them in their decisions. This could be done via explicit or implicit feedback, which I will introduce later. Here I outline different activities that can be detected in the climbing gym, and in the normal rectangle we can see activities which are detected in the literature, and in the dashed rectangle we outline activities which are not detected yet in the literature. This schema was proposed by Boulanger et al., and we extended his schema. Here we can see different activity recognition systems which employ sensors, and we can see that most of them are dealing with the sensors. For example, Climb BSN employed accelerometer placed on the ear of the person to detect activities of the climber. Then on the middle of the figure we can see two systems which employed wrist-worn accelerometers to detect activities of climbers. And the last but not least, project employed 5 sensors to detect activities of climbers. Then there are some recommender systems for training in sport climbing. There is a system called Beta Cube, which employed projector in order to detect activities of person in the climbing wall, and also they projected light in the climbing holds. Another project is called Interposer, where they detected climbers, beginners and experts, and they showed beginners how they will move if they were experts. For this reason, they used GAN's neural network. There are some already existing recommender systems in other sports, for example, running marathon training, where people employed the sensor to detect activities of runners, and they propose training plans to train for marathon better. Then we have fitness recommendations, where they detect when the person loses motivation for training. And we have hiking recommender system, where scientists propose hiking paths to hikers based on their preferences. Ice skating recommender system propose a time when the ice skater will finish the race on the data which is coming from the sensors employed while they were training for their short treks. We have recommender system for movies, which recommends you which movie to watch based on your likes or dislikes and based on your history of watching movies. And our question, can we do something similar for climbers? Climbers usually are interested to climb routes which are challenging, but within their capabilities, enjoyable, safe, within specified time. One important aspect is the difficulty level of the climbing routes. And our main goal is to understand climbers' needs and to provide recommendations according to their needs. Our solution is software architecture for climbing cracks and climbing routes recommendations. Here we can see that climbers usually use a climbing application called Vertical Life, and they record their ascents. And we call this data as logbook data. We use this logbook data to understand the climbers' preferences, and we match their preferences with the climbing routes characteristics. For this reason, we employed content-based recommender system, and we show recommendations on the map, and we show recommendations for climbing routes on the lists provided by the software solution. For this project, we employed several free software instruments. We employed Python, scikit-learn library, PostgreSQL. For developing website, we employed JavaScript, HTML, CSS, Flask, Bootstrap, and we used PyCharm, free version. And this is the example of the climbing recommendation. This is website, which you can see in this web link. We can, right now it's deployed in a way that you have to insert manually your preferences. But further step is to mine this application and to understand preferences automatically, so people do not need to enter their preferences. Here we also show, here you can see the map, and there are points for the climbing cracks, and with the red color we show the climbing cracks which are recommended to the user based on the preferences, and also we show the on the pop-up window on the left side gray window we show the explanation sentence why this route crag will be potentially interesting for the person, and we show the climbing crag name in the right pop-up window. This is the example of climbers' historical logbook data. We divided climbing routes in characteristics according to 4 different types: climbing discipline, climbing grade, climbing style, and wall steepness. And we measure how many climbing routes were recorded for different characteristics by the climbers in order to understand what they like. And the recommendations for the climbing routes within the crag are built as following. We create 3 different lists of recommendations for favorite moves, for training, and for motivational purpose. Recommendations for training. Here in this plot, I show 2 different climbers who recorded their climbing ascents according to climbing styles. And you can see that climber 1, which is blue color, mostly climbs endurance. So the ratio of climbing styles recorded endurance is higher than the other styles. And this climber avoids climbing technical and athletic styles. But climber 2, for example, which is red figure, shows that he climbs every style equally, and this person is trained more balanced. Therefore, recommendations for the climber 1 would be that this person should climb more athletic and technical styles, and maybe to climb less endurance. Recommendations for motivation. Here we deal with grade prediction model. In sport climbing, we have route setters who are climbers who initially build and design climbing routes, and they give difficulty level for the climbing route. But on the other hand, we have climbers who might have different opinion about the difficulty level of the climbing route, and they might perceive this route is harder or easier. And we would like to model this disagreement, and our assumption is that the routes which are easier than expected would be good for motivational reason, and we recommend those routes for the person as good for motivation. For this reason, we created this data set for indoor and outdoor routes, and the data is very sparse. We took this data from the mobile application, climbing mobile application Vertical Life, and we tried to build a model to understand the difficulty level predicted by the person to the route. We consider model as a rating prediction task, and we employed 2 models, linear regression and matrix factorization. Here we can see evaluation of the models, and we compared 2 models with the baseline model, where baseline model assumes that every climber would agree with the route setter and they will perceive the routes the same way. We can see that linear regression and random forest linear regression outperforms with root mean squared error of baseline. That means we can capture better the perceived grade of the person. Our future activities are to introduce implicit feedback, which is data coming from the sensors, to improve recommendation. Then further, we would like to evaluate climbers' opinion about the recommender system developed for the small subset of climbing routes. As been shown on the map, we developed this app for Arco climbing region, which is in Italy. And further, we would like to improve recommendations, taking into consideration the real feedback of the climbers. And further on, we would like to improve recommendations for training purposes, introducing this sensors data. Thank you very much for your attention. If you would like to test the website, you are more than welcome. And if there are any questions, I would be happy to answer. Thank you very much.
Okay, thank you very much for this presentation. We have a couple of minutes left. Are there any questions? No questions so far. I don't have a question. So one of the main things you're facing is that people give feedback after they climb, right?
Exactly.
So I think that's a huge challenge to make them insert the data, right?
Yes, exactly. It's a good question. Thank you, Martin. In this data, which is coming from mobile application of Vertical Life, we have feedback from climbers, and they leave feedback in terms of how they perceive the difficulty level. And if they, for example, think that this route was harder, they leave, okay, this route was harder, and how much harder was it? This can be learned by this modeling via linear regression. So we took this data to understand whether this route particular would be harder or easier for this particular climber. So yes, we mined vertical life application for this reason. Yeah, and still you can leave the feedback in the vertical life climbing up, whether you think that this route is harder or this route is easier, which is useful for data analytics.
To understand the data better.
Exactly.
Okay, all right.
Thank you very
Thank you
much.
very much. So,
Thanks.
thank you for this. We have 2 minutes left till the end of this track, so there is 7 minutes to the next talk. Thank you, and see you there. Very good. So welcome back to the Software Architects track at the SFSCon. Our next speaker is Maurizio Napolitano. He is the coordinator at the Unit Digital Commons Lab of the ICT Center of the Fondazione Bruno Kessler in Trento. And he will talk about the Apache Superset, so a modern data exploration and visualization platform. Welcome, Maurizio.
Thank you a lot. I am so if during my presentation you can listen some parrots, but the place where I am is very small, I have parrots to the other side of the door. So please, if there is a noise, it's not a problem, it's only some parrots, my colleagues. So Apache Superset, a modern exploration and visualization platform. This is my agenda. I start to explain to you what is Superset. To explain to you what is Superset, I start from the history of the project, because the history explains everything step by step, and is very nice. It's very important in this case, in this section, to speak about stack. And I want to explain you what is Superset by screenshot. So very, very easy to understand the project. I am here. I am also a developer. This is my GitHub repository. And if you go here in this banner offered by GitHub, GitHub recognizes me as a user, a developer that helped to contribute the Apache Superset. My contribute was not so amazing. I started to investigate Apache Superset 5 or 6 years ago, and my contribute was very, very small. My contribute was only in the translation in Italian language. But I am happy to see that my idea to start with a superset is a common idea. A lot of people now like to use superset. And superset from the 21 January was a big announcement by the Apache Foundation, because now is at the top level project. After the announcement, a lot of people around the world started to speak more and more and more about superset. But this was not so new, because superset used by a lot of very famous company. You can see here the company, and you can understand the power. Players started to use superset. There is a reason, there is a need. The need is the data visualization to understand better what is inside the data. Apache Superset is born in the laboratory of Airbnb. Airbnb started to say, we need a system to visualize very, very fast the data in our main more important database, Druid, a database, a NoSQL database, very, very fast. And by using different projects around the world, by Tableau is one of the first they started to say to the people in Airbnb, say, no, we need more, we need to understand better. So start the story of Superset. The first name of Superset was Panoramix. Later changed the name in Caravelle, and now it's before to be Apache Superset was only Superset, and the 21 is the first level project in Apache, because the project started to be an open source project. The license uses the Apache license, and in very, very fast time, there was the acquisition inside the projects of the Apache Foundation. So Airbnb started to say, I need to read the data from Druid, druid.io. I need a Panoramix, I need a Druid. So started with Panoramix. Some people say that is a hackathon inside the Airbnb group. But what is nice is that after the first board of the code of Panoramix, in this case, was already online in GitHub with the open source license. They started with the right way to speak about open source, to create a community, to use a license, to share the data and the code. Very, very fast. And after working with the Druid, they start to say, yes, but maybe there is not only Druid. We can use other kind of database. And Panoramix started to be wrote in Python. So Airbnb said to say, okay, starts to say Python, we can start to speak with the Druid about what is one of the best solution package to speak together with the database. There is SQL Alchemy. So with SQL Alchemy now, we can navigate all different databases. So they changed the name from Panoramix to Caravelle, because moved the point of view. The first point of view was only to have a data visualization from Druid. Later was an improvement on the architecture by using SQL Alchemy, and say, now we can read any kind of database. Any kind of database means that you can abstract all the data. And if you abstract the data, you have different visions. So if you have different vision, you can join with Superset all different kind of data set. So you can create a superset. And with Superset, so you can choose different kind of sources with different kind of databases and have inside your platform. And later from here, you have different table, create your table, create the view, create what you want. And from here, you can start to investigate the data by analyze each data set, each table, by create the data visualization in different way. Later I'll show you better. And also manage all together with a dashboard. Dashboard with another power, because behind the Superset, you have also everything connected with the ACL, the access control list for the users, because you can choose the different provider, I speak about users, with different access, and later you can define your dashboard. But not only, there is another surprise. It's made everything is based on Flask. So behind, from the data of Superset, you can create also REST API. And you can investigate the data that you can extract from the data from the table, and you can have your view of the database in different way by only one data set or different data set, but abstracted. The answer is you can obtain this in CSV or in JSON, and you can create your representation. Or you can read here, Superset is one of the best tools used inside Airbnb. And the production says we have every day we have more as 100,000 charts. We manage this. And if you think about the analytics inside Airbnb, if you think this kind of company, they have to understand the behavior of the users, all the possibility what the company offers. So in a short time, can have everything in a summary made with the dashboards. But it's not all it is. I showed you other wonderful player like Netflix, for example, American Express and other. So now everybody can use Superset. This is the task. Or you can see the backend is made in Python, and is used with Flask. With Flask, you obtain not only the possibility to create the web page, the web service, but also to have all the REST API, and to manage very, very fast, because it's a framework for the web development, also the users and other. So you have a big piece to be very, very fast in the reuse of the different sources and also different components. Behind, there is SQL Alchemy, I told you before, so you can join different kinds of database. And for the analytics, there is the use of Pandas. Pandas is a package very, very famous in the world of the data science. And the goal of Pandas is to analyze data set. So what is possible to do with Pandas, with all the methods that you can use, all the analysis you can do, is possible directly to do in Superset, but with the difference that you not need to know the code. You need only to say, this is the database. Okay, you need to understand a little bit of statistics, but not so amazing. For example, mean, sum. What you can do with if you use a software like LibreCalc, if you use a spreadsheet, is the same. You can compose, analyze the data directly from the web interface. Behind, this is the behind. The front end is made everything in JavaScript. The main component is React. The production of the graphs, the charts, is made with D3, but there are other kind of library. For example, there is a Kepler.jl. Kepler.jl is a library made by Uber to manage geospatial data, with also the time variable. So, for example, with Kepler.js, if you have the time, you can understand the movement of a car during the time if you have the data. One of the goals of Superset is to manage data in real time. So the first approach in Superset is also to have always a column with the timestamp. So you can read the data and investigate the data during the time. This is the list of supported databases. All the databases supported are the databases behind by SQL Alchemy. But you can spend a little bit of time to read the names, because there are some names, for example, SQLite. It's easy if you want. It's very, very, very smart. Is a flat file. In Superset, you can upload CSV file, and the CSV file are transformed in SQLite. But there are other kind of products, proprietary and open source products. So you can also use some services like Google BigQuery, or also some database like PostgreSQL. It's very, very nice, because you connect only, you have only to write all the needs. So, for example, the name of the server, the user password, the database table, and later Superset manage your dataset like a table, and you have the dataset without problem. This is the workflow. So from Superset, you can choose different sources. After you choose the sources, there are different tables. So you go inside to the tables, you can see everything like a table. And from the table, later you can choose one chart. So if you stay in this direction, you can start to analyze only one source directly from a superset. Data table, add the table. You can create a table because you can say, you have different sources, you can create a view. You choose, for example, if you have a common key, you choose the data from a source with another source, you join together, you create the table, and later from the table, you define the data visualization. You can choose different kind of data visualization. There are a lot of data visualization inside, and you can start to investigate the data. After the data investigation, you can create a single widget. The name in Superset is Slice. You have different widgets, and later you have a big area like a canvas where you are like a painter, and you can decide the position of each widget. Together with each widget, you can also add some information like text, like images and other. Is a common way used by other proprietary software, like, for example, Power BI, like QLink and other. But this is open source. And the expansion, what is possible to do is wonderful. There is another possibility. Between the widget you can use, there is also the possibility to change the behavior of all the widgets chosen inside a dashboard by a variable. If you can say, okay, I choose a different, for example, you create a dashboard with a table, a histogram, a sparkline, okay. And later you add a filter. So the filter is the name of, you define the variable, and if you change the variable, all the widgets inside around changed. And this is transparent. You have only to define what is the common key, but the common key you start from the table. If each table has the common key, later the filter is the same behavior. So the steps are very easy. Define the source, define the data set, and you can create a data set by aggregate data set. Define all a single chart for a table. So for a data set, you can choose different charts with the same data, because maybe you like to have the representation as a table and also the representation as stacked bar. And later you can compose your dashboard. The dashboard, later, you can define the different kind of users. Everything is online, is a web service, so everything is by web, the interface. You can use inside your laptop, or you can install in a server and other. Luigi?
So time will be over. If you want,
Sorry.
you can wrap up quickly.
Yes, very quickly. I wrap up quickly with some pictures. This is the representation of what you can do with the Superset. So this is one example of a dashboard. This is the possibility to choose different tables. Here, all the kind of possible charts you can use in the Superset. And here, the possibility to create a custom SQL query inside Superset. So if you want, there is a demo, but I stop here. You can create and visualize everything without the knowledge of SQL and Python. You can manipulate very fast different kinds of database. Some problem is that it is a growing project, but now is always better because there is behind the Apache Foundation. And one of the difficulties is to plot aggregation of either level without some data manipulation or creating view. Here, in this point, is one of the disadvantages, but I think if you stay on the left column, you can create very, very fast, wonderful, and amazing dashboard.
All right. Thank you very much. Very impressive what you can create here. Thank you for your talk. And so we are over time, so there is no more time for questions. Thank you for this. And you have 3 minutes for moving to the next track or to continue here. Thank you. See you soon.
Thanks a lot. Thanks a lot.
All right, welcome back to the Software Architects track of the SFSCon. We have our next speaker here. His name is Simone Trentini. He's a technician at EURAC Research Sensing Solutions, and he's talking about the environmental data platform web portal, which should provide the tools for discover types of data available for processing big data sets and visualize them. So, over to you.
Thank you very much. Good afternoon. I am Simone Trentini. I am software developer of Center for Sensing Solution in EURAC Research. And I'm here to present you the environmental data platform web portal that is born from the, is an idea born in the project FESR DPS4S Lab. We started to develop the portal from an idea and the needs of our researchers in EURAC, because the researchers usually has these three problems when they start their research. Where is the data? How to get the data? And then where to process the data to perform the analysis. Our idea and our solution is to create a web interface, a gate that allows the researcher to access easily to the data. In particular, to enter in our infrastructure that I will present you in the next few slides. This is the portal. You can start to play with it because it's already online. And the portal, as I said before, is the gate, the main entry of environmental data platform that EURAC developed during the last years. It is a big platform composed by a lot of components, and thanks to the work of my colleagues in Earth Observation and also in Center for Sensing Solution, we try during the years to organize in the best possible way the platform, starting to set up the data repository, in particular following the needs of our researcher. For example, we set up time series databases like InfluxDB, common SQL databases. We set up raster data management databases. Also repository like GeoNode, that is a platform that allows to create maps using layers, vector and raster layers. Then another important part of our platform is the backend system it's composed by our processing platform in software like Jupyter Hub and OpenEO Web Editor. An important player is the metadata catalog GeoNetwork. Small parenthesis, metadata is the information of the data. From now I will speak of metadata, referring to the piece of information, a bunch of information that describe where are the data. And the name, and in particular, where are the data. So the researcher can access to the metadata catalog to find the data. Another important part of our platform is the front end, composed by many APIs, web application, general web services. And in the last years, we develop also and improve the authentication and authorization part using Keycloak in order to improve the security of our platform and organize the access and the authorization of the data to every user. The platform, but also the portal, are oriented using following the FAIR data principle, and we promote to the creation and of the FAIR data. The data, because in this way it is possible to manage in the best possible way and also to share knowledge in a good way among the researcher and among the projects. The data simply should be findable, so the research has to find the data in an easy way. The data should be also accessible in an easy way. Interoperable means that the data can be managed and used and processed by different platforms. And reusable, this is related also to the license and the possibility to share the results and the data itself. This is a small parenthesis. Now I come back to the ADP portal architecture. That is also the portal is FAIR oriented. The ADP portal is a web application, so it has a common web application architecture. We have a front end, the back end, in this case, developed by Django, and it access to a data repository, in this case, in particular, to the GeoNetwork metadata catalog that I mentioned before. It is important, I want to underline that the portal try to show in an easier way respect to the catalog all the data available in our platform. Now I will show you the features, the main feature of the portal. We have four main features and characteristics. First of all, that I said before, is that the ADP portal is an access point for our platform. So the user now can access directly from through the portal and access to our environment. All the other components are still available in a single way. So if you, for example, know the link to Jupyter Hub, you can go directly to Jupyter Hub and use it. But the portal help the new user, also giving them a sort of flow. The first step is the search, then the detail of the data, and finally the process. The second important feature is the discovery of the data. Querying the API of metadata catalog, the user, the portal shows all the available data in our platform, and the user can search by keyword, category, drawing a bounding box on the map, and also setting the time range if, for example, the researcher want to find time series data. Another important aspect of this platform is that it is a collector of documentation. During the year, the researcher produces a lot of documentation on how to use the data and about their projects. So we try to create a list easily to access where where the researcher can eventually find the documentation that he needs about the research that he's doing in that moment. All the documentations are categorized following the same categorization of the data. So, for example, we have category for APIs, source APIs. I don't know if you know that, OpenEO. So we have different categorization that can help and improve the search of can help the researcher to see in the documentation list in the best way. The last but not least important feature is the creation of snippet codes, because one of the needs of our researcher is to find the data, but then maybe one important step is start the process, start the analysis. After the search of the data, we provide a piece of code that the user can simply copy and paste in his environment, local environment, or also in the Jupyter Lab in our platform. For example, here you see a brief example. We have the name of the collection, the bounding box, where the data is collected, the period, and in the lower part you see the piece of R code already customized, ready to use for the research. Finally, I want to conclude with a good news. The federation of our platform with the Open Data Hub developed by Neutech Park. Thanks to the work of our colleagues and the Neutech Park colleagues, now it is possible to access to our ADP portal with and to Open Data Hub with our own login. And we can start to use both the data of Open Data Hub and vice versa. The users of registered in the Neutech Park can use our platform and our services. So this is a good way to improve the share of the data, the knowledge among these two big platforms. So thank you very much for your attention.
All right, thank you very much, Simone. Are there any questions here from the audience? No question? We have a question from an online question. I will read it anyways, so in part, it was maybe already answered. It's about the overlap between the Open Data Hub and your work. So if there are any synergies, so you mentioned the login there, maybe you can tell a bit more about this.
About the federation?
About the overlap and the collaboration between the Open Data Hub and your work.
Yeah, the idea behind this federation is to allow all the use, because Open Data Hub offer a lot of, a big set of data, and maybe they can be useful for our researcher to improve their analysis and their process, their projects. And also we have a lot of services and data that can help other users to yes, to improve their work. Yeah, that's it.
Okay, so this kind of not a replication, but a kind of a proxying of.
Yeah.
Yeah. All right. Okay. So, are there more questions? Otherwise, we could stop here. Thank you very much, Simone. And we see each other again in about 7 minutes for the next talk. Thank you very much.
Woo!
Now we have our next speaker. His name is Andrea Antonello. He's a software developer and the co-founder of the company Hydrologis. And he will talk about the integrated modeling with KLab, which is a knowledge laboratory. And the goal is to link knowledge across domains of single modelers and scientists. So, welcome.
Thank you very much. Good evening, everyone. Thanks for being here. Today, I'll have my hat on of a project that's called ARIES, which stands for Artificial Intelligence for Environmental and Sustainability. So, ARIES is a project that dates back in 2007, where artificial intelligence was just a buzzword and not so well understood as today. As of today, it starts at the University of Vermont with fundings from the National Science Fund. And throughout the time, it had several players that contributed to this project. Two big changes occurred throughout this project, and the first being the visionary of the project, Professor Ferdinando Villa, that moved from the States back to Europe and found its place in the Basque Center for Climate Change. And there recently, at the moment, the headquarters of ARIES and KLab, as we will see, resides. The second and very important thing that happened is that a couple of years ago, the United Nations System of Environmental and Economic Accounting, which is a big, big thing about economic accounting, decided to base its SIA on KLab, and that gave a huge push to the project. So what is KLab anyway? It stands for Knowledge Laboratory and actually is a full stack solution that should enable the integrated modeling, which means not just execute models, but also be able to produce models, curate models, link models together and deploy them. What does that mean? It could be scientific artifacts as models themselves, but we're talking also resources, data sets, whatever is necessary to do modeling. Because one of the big problems in modeling is if you're into modeling, you write a model and maybe in the end you have like 3% your model and the rest might get being all boilerplate code. To do I/O, read and write rasters, read and write vectors, do whatever, take from databases. Then there is a lot about visualization. And then if you walk around a timeline, you do, I don't know, hydrological processing, then you will also have the issue about the timeline, and that gets even worse. So in the end, usually you end up to have a big monolithic code, and doing integrated modeling with other models, I don't know, groundwater with superficial water with meteorological model gets extremely difficult. So Caleb tries to change things in the fact that you're only allowed to define your quantum of knowledge. And you can put that quantum of knowledge semantically annotated in your network, and when that network gets the model, there is a resolver that will, once you want to observe a particular concept, being it a hydrological or whatever else you want to observe in the world, it will resolve, create a data flow, taking the most suitable quantas and make them work together to produce a data flow. So the stack itself is composed of a couple of server-side components and a couple of client sides. The engine is kind of the heart of Caleb because it contains the resolver itself, the brain that puts together the models. Then there are the K-nodes. The nodes are more like a storage, but a storage of knowledge. You can place their data sets, true. You can place their semantically annotated data sets. You can place models. And every node in the network will concur and provide you with models and data. Clearly, there is the need for an orchestration, and that is done in the hub. In the hub, you can get credentials, and the hub synchronizes the different nodes. And then there are two clients. One is the Explorer, as we will see, graphical user interface for users, and the other one is the modeler, which is something for scientists that will produce models that will, something like this, you create your data, you add your metadata, and you are then able to define your data in space and time clearly, because some data change in time, and then you can publish it to your network. So to try Caleb, you can go to integratedmodeling.org. There is a getting started page, and there you can also get a certificate. As I said, there needs to be a network where models are there, where data sets are there, and the Integrated Modeling Partnership Network does that. It gives you the possibility to register and exploit what has been built by several scientists already. So what you download is a control center from which you can start a local engine if you want to do your own modeling, and a modeler. From there, you can access the Explorer, which is nothing else than a spatial context, which is very used for any user, like a map. And in there, you can also define a temporal context. So from there, you can run your models. For example, let's start very quickly, very simply. Suppose you write into the query, you can use near English, near natural English. So you start writing elevation, and it will propose you events or elevation or attributes. And if you run them, very simple, it will show you a map of elevation, which looks something extremely simple, but behind the hood, there is a lot, and you will see. So you can enhance it. You can use operators, arithmetic operators, for certain kind of qualities, like elevation. You can say elevation major than, and it will just cut it off. But you can also use other operators that change and convert the type of concept. So, for example, distance of city. City is a subject and is the position of a city, and distance to city gets a map with, in every point, the distance to the nearest city. Or presence of mountain peak, which would mean, is in that point of the map a mountain peak, and it will just create a map with that. But you could also say, let's do something a bit more complex. Land cover type. Everyone knows it's a map that has the land cover type in each pixel. You can ask the system, give me the land cover type, but without some of the attributes of the land cover, like water body, and it will create a map, but without the water bodies. At some point, the Explorer, the queries you can do through the Explorer, reach a limit. So if you're up to more, you need to open up the modeler. In there, you can do anything. And for example, you could model, you can create your own model where you model, for example, the level of elevation, observing the elevation and classifying through a lookup table. Just like this, you define and you have some classes. We'll see later where those come from. And the result would be a classified map directly. If you need to give it a spatial and temporal context, you can do that by this upper observe part where you observe a certain region. And in that case, then, it would just work on a single part of the map. And that's the thing. We are talking global here. I don't know if this is clear. This should be clear because we are talking about something that works over the whole world. And this is clearly something quite difficult. And they were talking about the FAIR principles before, and we also embrace FAIR principles completely. So you have at the top, you have a couple of tabs where you can just access the data and the data flow. The data will show what exactly are the data that have been used through the process. So you have been doing an elevation model, well, you will have global elevation data with all the metadata. You know exactly what has been used to generate your result. But not only, what is the model that has been run? What exactly happened? So in this case, it was very simple. We were doing a classification of an elevation map. It tells you that it's pulling a WCS resource, which is a geographic standard to get physical data, and then a lookup table is applied. If you click on it, you will see also which lookup table has been applied. And this is quite cool. And I will show it in a different manner. So since we're talking global, how can we use global data if they are different everywhere? Not so many data sets are global. For example, land cover is not global. We have different data sets, but if you look at the type at that particular region and you say land cover type, you will get a map of land cover. So what's happening here? Let's have a look at the data, and we will see that there are two types of data. One is the classic Korean land cover, and then there is the climate change initiative land cover. So how are these two harmonized? Not only in resolution, but in classification. They are different. So what happens is you look at the data flow and you will know exactly what happened. The resources, two different resources were merged, doing two different classifications. And classifications towards something that has to be common. And what is common? The different water bodies, inland water bodies, these are the attributes that are part of the worldview of KLab, which means KLab has a worldview which is a whole set of semantically annotated concepts that start from the very bottom to build up to different sciences. So any word, you have to think as a language, any word that you have in there has been defined. And vice versa, if you go down to the bottom, any word like area, linear has been defined. And when you come to the very bottom, it goes down into ontologies. So maybe someone was thinking, where are the ontologies? Here is where they are, because somewhere you need validation in this process. Because otherwise you could ask elevation in kilojoule, and that would just not work. Or you could ask land cover type without elevation. This doesn't make sense. So it's still all validated, and while you write your models, you will get syntax errors if you're not doing something that makes sense. We have changes in time very quickly just about real modeling. There is, from Copernicus, for example, this weather processor models Copernicus data and will define for you concepts about rainfall, temperature, solar radiation. And from that moment on, you can just, well, look at the maps, which is nice but not really useful when you do modeling. But most of all, you can write your own model, your own runoff model, your own infiltration model. You need evapotranspiration, well, then you will need solar radiation. Data like this, you write just your model and let KLab do the rest. You will tell you that your model observes other qualities, which means it depends on rainfall data, on temperature, on solar radiation, and Caleb will generate the data flow to extract the data of solar radiation or whatever is necessary at the right resolution, at the right time step for you. And in the end, it will make your model work. I will cut it here. For developers, if you're interested, there is an umbrella organization, GitHub, called Integrated Modeling, and that contains the complete source code and also some examples, and very important, the definition of the worldview, because without that, you can't model even a line. And last but not least, in 10 minutes, I think it's quite difficult to explain something like that. There is a presentation of the release of Areas for Sea Explorer of the UN, and I think if you're interested in ecosystem services, you should definitely have a look at that video where everything has been explained of how Caleb really works, the semantical part, the ontologies, anything. So thank you very much.
Thank you very much. Do we have questions? No questions so far? Okay, so thank you again. And we have about 5 minutes for the next track. Thank you very much.
Okay, good evening to everyone here and people following my presentation online. I'm Alex Boieri from Maptech, and today I'm going to present you my master degree thesis developed under the supervision of Professor Melgani of the University of Trento, a group of FOSS and Maptech. I'm going to speak about artificial intelligence algorithms for the automatic segmentation of multispectral UAV imagery. So the project in which I developed my thesis was the Drone Trap project, founded by the DEVA Horizon 2020 program, and aims to develop a support tool for farmers to reduce the waste of water and fertilizers in the agriculture. So we are going to integrate UAV multispectral data with photo trap image acquisition to gain an economical saving as well as a better quality of good and improvement of working condition of the workers and preserving the environment. So the project was proposed by FOSS, a leading company of a small group of small medium enterprises in which field of expertise is in IT and electronic design, and Maptech, a research-oriented spin-off company of Politecnico di Torino, which develops and prototypes drones with innovative aeronautical solution for aerial surveillance as well tactical operation, including obviously precision agriculture. Both the companies are incubated here in Neutech Park. So the main objective was born from the need to recognize and segment rows pixels within orchards to evaluate the vegetational health status of the orchard itself on single parser. So we wanted at the beginning to accurately segmentate the pixels between rows and the background, so everything else, by avoiding misclassification that could be caused by, for example, grass, shadows, or other objects, as you can see in this image. So in general, we employed an unmanned air vehicle, the Maptech Q4E quadrotor, so a quadrotor developed by Maptech, which has a maximum takeoff weight of about 4 kilos and can carry about 600 grams of payload. The payload is a multispectral sensor, the Mica sensor at the GEM, which is a multispectral sensor with 5 spectral bands in 5 different optical sensors, and is also equipped with an integrated GPS and light condition sensor, as well as a calibrated reflectance panel. So the algorithm I'm going to present you today are based on 2 different solutions. The first one is a super vector machine, which is a machine learning methodology well known in literature, and is based on a few hyperparameters to be tuned, and needs also a small amount of training samples to be tuned. It has many different implementation through open source libraries. For example, in this case, I implement in scikit-learn Python module. The second solution is a convolutional neural network, another well-known solution in machine learning and artificial intelligence, which has a full classifier architecture customization, and with respect to super vector machine, has a better spatial coherence management. Instead, it needs a huge amount of training samples to be trained, but has also convolutional neural network have many different open source implementation. For example, in this case, I use the PyTorch module again in Python. So some more details about the 2 methodologies. The SVM is a technique proposed in the early 90s by Vapnik, and as I said before, is really powerful for both high and low dimensional feature spaces. So it defines hyperplanes that separate the different classes, and as I said at the beginning, it needs really few training samples to be trained. So in this case, I consider 5 input features, which are the 5 multispectral bands of the multispectral sensor, and the classifier produced in output a single binary classification value segmenting between rows and the background. Regarding the CNN instead, which is really suitable for image classification or segmentation, I implemented the UNet proposed architecture in 2015 by Ronenberger, which was proposed the first time for biomedical RGB image segmentation. In this case, again, we have 5 input channels as the 5 input feature for the network architecture, as you can see in the bottom right image. These 5 input channels are processed with contraction on the left part of the architecture and then expansion part or layers of the network. And in output is produced a binary map representing the 2 classes. So in white, you can see in that image where we have the white polygon represent the raw pixels as the black polygons is the background. So generally, the processing flow chart is similar for the 2 methodologies. We have the input data, which are, as I said, the multispectral bands, 5 multispectral bands, with the canopy height model. The canopy height model is the height data of the canopy of the field, which is used in the CHM thresholding we will see later. So in input, we have this data, which is cropped and on which are applied some kind of data scaling, data flattening, and other pre-processing operation depending on the the classifier requirements. Then we have the prediction with SWM or CNN, and the predicted binary map is then filtered or thresholded with the height with values defined on a priori analysis. This THM thresholded binary map is finally filtered again with a morphology filtering operation, which is needed to remove some little spots and some little errors so to fine-tune the binary map. So the experimental setup we considered was based on the first generation of the 2 data sets. So by a random point data sampling, we generate the training, testing, and validation data set for the SWM classifier. Then this data is filled into the training and validation algorithm in case of SWM, and these models, these generated models, are finally tested with the test dataset to produce the performance results. Regarding the CNN classifier, the generation of the dataset was done by dataset manual annotation. So I manually generated the polygons representing the raw pixels on the orthoimagery. This data was filled with the multispectral orthoimagery in the training algorithm for the CNN classifier, and then the CNN model was finally tested with the test dataset. And these results are compared, and now we will see the results with the SWM performances. So regarding supervector machine, we saw that the direct classification without filtering and thresholding, so without applying CHM thresholding and morphological filtering, reached an F1 score of 0.6. The F1 score is a similarity measure commonly used in literature to compare images with their respective ground truths, and their values go from 0 to 1. So 0.6 on average is not that good. This is due to the presence of many false negatives, as you can see in the first light blue circle, and also by the presence of many false positives, the second light blue circle. On average, we saw that the best results was achieved with an F1 score of 0.81, 82 more or less, with the post-processing application of CHM thresholding and morphological filtering. Regarding UNet, so the CNN classifier, the direct classification reached an F1 score of about 0.84, 85, which is really, really good with direct classification. Then we implemented also the CHM thresholding as for the SWM case, but we saw that there was a significant reduce in the F1 score caused by the reduce in the recall value. And instead, with the application of the morphological filtering, only the morphological filtering, we saw that there was a slightly increase in the results because this type of application is used to remove some little spots of misclassifier area which can gain better results. So in general, we have to say that the accuracy results I'm presenting you now could be affected by manual mislabeling errors I do at during the dataset annotation. For example, you can see in the light blue circle there, the blue polygons is the ground truth manually generated by me, and the white polygons are the output of the CNN classifier. You can see that in some cases, the CNN classifier could perform and follow better the shape of the rows better than what I did. So by comparing the two methodologies, we can say that overall UNet achieves an higher F1 score with respect to SVM, even without the post-processing operation, so CHM thresholding and morphological filtering. And so to be practically applicable in real scenarios as we wanted, the SVM requires a relevant post-processing. So you can see in the image there is a comparison of an area of the data set that we consider and acquired and analyzed, comparing the results after the SVM classification, CHM thresholding, and morphological filtering with respect to the UNet classification with the morphological filtering only. Regarding the speed, on average, we saw that SVM requires, as expected, less time to be trained as well as to predict. So it's more or less, we can say, 3 times faster than UNet. Even that, we tested also the two architectures on GPUs, so graphic accelerated hardware, and we saw that in that case, UNet could perform 10 times faster than SVM. So as a practical use case, with GPU in this case, we can say that with our methodology, we can segment and so analyze 1 hectare of field in more or less 4 minutes with an SVM and more or less 10.5 minutes with the UNet. So to conclude, we consider to have developed an accurate tool for automatic segmenting row in multispectral orthoimagery by avoiding what we expected at the beginning, so the inter-rows, for example, and or shadows misclassification. Because of the high-resolution images we acquired, so we use data of more or less 2 or 3 centimeter per pixel resolution, we understood that SVM, by performing pixel-wise classification, is not that suitable for our application. So with the application of the post-processing I showed you before, we can avoid most of these classification errors. Another important aspect is that multispectral data usually, and as we said at the beginning, the UNet classifier was developed with RGB data at the beginning, but we applied multispectral data, even that the multispectral data is unnecessary sometimes for applying image classification, but with a single survey, in this case, we can perform multiple operations, so we can retrieve multiple information from the same data source. So with a single survey, we can retrieve the segmentation map as well as the vegetational index status you saw in the first slide. So to conclude, some additional improvement we are considering now is the integration of further and further data, obviously to reinforce our models because we need more data to fine-tune our solutions, as well the introduction of some automatic adjustment of the output threshold, for example, for the UNet classifier. So thank you very much for your attention, and if you have any question, I will be really happy to answer. Thank you.
Thank you very much for this presentation. Thank you. Are there some questions from the audience? No questions so far? Okay, so thanks again. See you next time. We have now 3 minutes left for this 15 minutes presentation, plus 5 for the next, so means 8 minutes for the next track. See you then.
Woo!
Welcome back to the Software Architects track. We have our next speaker. His name is Alex Meana, and he's a student in the TFO Bolzano. And he's showing a project where they track climbers using stereo cameras and analyze their activity, and he will present the first prototype of his. Welcome, Alex.
Thanks a lot for having me today. So, the title of my project is called Tracking Climbers Using a Stereo Camera. And as probably many of you already know, climbing is a big part of our culture, not only in the locals here in South Tyrol, but also tourists come here just for climbing. And because of that, we thought it would be a great idea to give the climbers more opportunities to save themselves and also to challenge themselves even more. So the whole project is called SALSA. This stands for Sensors and Data for the Analysis of Sports Activities. And here you can also see the little logo I made for our project. So the overall goal of the project is to be able to detect a climber's activity inside of a climbing gym. This is once to provide feedback to the climbing gym's owner about any type of problem that might occur. For example, someone could be stuck on a route, or someone could fall down and maybe hurt themselves. But it is also nice because like this you can detect the popularity of certain climbing routes. So the climbing facilities owner can always improve the options to give the climbers. So, just for context, as has already been said, my name is Alex Merano, I'm 17 years old, and right now I'm still going to high school. I am attending the 5th year of the Max Valier here in Bolzano, and during summer of this year, 2021, Professor Janes Andrea of the Faculty of Computer Science here at the University of Bolzano gave me and my friend Ralf Bardacher the opportunity to work in an internship. And this is the task he gave us. So, the whole project SALSA is very, very big. And our little sub-project is just about identifying the activity of a climber using a stereo camera. We want to identify if a climber is falling, climbing upwards, downwards, left, right, or maybe taking a break or falling down. You get the deal. And furthermore, we want also our application to be used to measure the amount of time a climber needs to finish certain routes. Like this, even experienced climbers can be able to always challenge themselves and push them to give it their all, because they can see where they have to improve themselves and where they need to practice a little bit more. And like this, we can also give feedback to the inexperienced climbers and maybe it'll even help them if they fall and give feedback to the climbing gym's owners, so they could even call an ambulance, for example. The hardware we used for this project was a Z2 stereo camera by the company named Stereo Labs and a Jetson Nano. We used a Jetson Nano instead of a Raspberry Pi because it has a GPU, and we need this GPU, or better said, the CUDA cores, to run the applications from the camera. And we used this camera, the Z2, because it already gives you predefined algorithms that we used to identify the activity of a climber. And with these algorithms, a lot of work has already been taken off of our shoulders. So here you can see both algorithms that we used in our project. At first, we used the body tracking algorithms. And I think it's really cool because you can see every limb of the climber. For example, you can see both legs, both arms, and even the ears and the eyes. But the problem we found by using this algorithm was that after a distance of about 5 to 10 meters, it wasn't as accurate as we needed it to be. So instead, we used the body tracking, the object detection algorithm. That's the one you can see on the left. For example, here in the picture, it's detecting a dog, a bicycle, and a car, but we only need humans. So we changed some variables inside of the code that Stereo Labs already gave us with the camera, and so we only detected humans. After we were able to get the data from the camera, we started logging. So the data we received from the camera were three-dimensional coordinates of speed, size, and distance of the object we're detecting. And we logged this into our safety files and saved it also for furthermore applications that might come into this project. After we saved all of our data, we started with the anomaly detection. For example, here in this graph, this small dot you can see in the top corner is an anomaly. We calculated the anomalies by calculating the standard deviation, and the anomaly is the average value plus 3 times the standard deviation. And if a value falls out of this range, we detected it as an anomaly. For example, if this were the data of a climber inside of a climbing gym, and this value would occur, we could send feedback to the climbing gym's owner about someone maybe falling down or getting stuck somewhere. Our testing phase wasn't this big because we only had 2 participants. So we went towards the camera, we went away from the camera, we went left, right, up, down, we jumped around, you got the deal. And after our testing phase, we were left with our first prototype. The prototype consists of our Jetson Nano, our camera, and a browser application. So, as you can see here, on the Jetson Nano, there's a log file and a web server. And the camera is sending constantly data about the object it's detecting to the Jetson Nano. And the browser is taking this data and is producing this visualization that you can see on the left. I coded this visualization in JavaScript. The x-axis is, like you can see, to depict the time, and the y-axis is for the distance of the object from the camera. The green color here is for slow movement, the orange color is for moderate movement, and the red color is for fast movement. For example, here the climber, at first he started going away from the camera kind of slowly, then he ran a little bit towards the camera, that's the yellow line you can see going down, then he went away again, a bit slower at first, then a bit faster, and then he ran suddenly towards the camera really fast. That's the red line you can see over there. After this, the climber stopped and just walked towards the camera a little bit slowly, away again, and then finally he walked towards the camera again. I hope you liked my little presentation, and if you have any questions, feel free to ask me anything.
Okay, thank you very much, Alex. Other questions from the audience? We have some time left. Yeah, please go ahead. Could you come out to the microphone?
Hi, so I'm Davide. I have a small question. Where will you place the camera? Like on top, behind, I don't know.
So we already thought about this problem because we can't just put the camera on the floor. Because if someone's going to fall down and fall on the camera, once the camera's going to get broken, and second, the person's going to hurt himself even more. So we thought about maybe installing them on the ceiling or another climbing wall. But we haven't thought about it that much because right now we're just planning on how to run our algorithms, and in a further phase of the project we're really thinking about how we could really implement those inside of a climbing gym. Another problem like this we faced was also with privacy, because you can't just film people inside of a climbing gym. That is against the privacy laws. And because of that we also need to reassure the climbers, or maybe make a contract with them, like if they're really, really okay with it, and so on.
Okay, thank you.
All right. Are there other questions? I have one question. So in that case, you have to know how the wall is built, right? Because if the wall makes a curve or something, you have to consider that as well.
The thing about the camera is it gives you 3-dimensional coordinates, so not only of x, y, but also z. So you could not only see where the person is, for example, if you have this screen, not only where on the screen it is, but also how far inside it is. So like this, the camera would already consider how far someone is away, also from this angle.
Okay, so can extract this from the data. All
Yes.
right. Okay. So if there are no more questions, I'd say we stop here, and thank you again, Alex.
Thank you.
All right. So we are heading towards the last presentation in this afternoon, and software architects track. And now we have Roberto Confalonieri, which is an assistant professor at the Free University of Bolzano, and Boyuan San, he's a research assistant. And the next talk will be about a hyperspectral image classification for wood recognition. So welcome to you.
Thanks for introduction. So as introduced, this talk will be about hyperspectral image classification framework for wood recognition, and this is work is carried out in the context of FREFESR project called hyperspectral images for inspection applications. So this project is a collaborative research project between the University of Bolzano, the Faculty of Computer Science, University of Bolzano, and Microtech company. And it has essentially two main objectives. So on the one hand, to develop a platform for the acquisition of hyperspectral images. We're going to see in a bit what an hyperspectral image is. And on the other hand, the other objective is to develop or to adapt existing deep learning frameworks to deal with such hyperspectral data, since they are not, let's say, ready to do so. This is a local project, as I said, but would like to point out that is also an international collaboration effort, as you can see. So many members and collaborators, they took part in this project, and from Italy, India, and Myanmar. Okay. So what is an hyperspectral image? So I will start talking about normal images. So as all of us might already know, RGB image is essentially an image which human eye can perceive according to a certain visible wavelength range. And this image in a digital way is represented through 3 different bands, which corresponds to red, green, and blue. And as you can see here in the slide, there is a representation of this cuboid of an RGB image in the, for instance, when we want to process it for any classification task, for instance. Okay, this is the way, the standard way in which images are presented. So what is now an hyperspectral image? Well, an hyperspectral image is a much richer image where we don't only have 3 bands, but we have much more. And this is possible essentially because hyperspectral images capture information which is behind the visible spectrum. So it's information that our human eyes, they cannot perceive, but they can, of course, represent it in a digital way. And so for each image, we don't have, for each pixel of the image, we don't only have 3 bands, but we have a variety of bands, which is called here a multitude of vectors band, because it depends on the device that you're using to acquire these images. This number of bands can vary, okay? So not specifying a specific number here, just saying there is a lot of information in the spectral dimension for these images. And what they can do? Well, they can identify, represent object and diffraction of objects in such a way that we cannot perceive with the human eye. So, once we have represented this information, it is interesting to understand how to exploit it for different tasks. As I said, you need to have specific hardware, in particular specific cameras or sensor, which they are able to capture this multitude of bands. And once you are able to do that, you essentially have, as you can see here, an image which, instead of having only 3 bands, it has, as I said, a lot of them. So as an example of which what an hyperspectral image look like, if we render the different bands of these hyperspectral images, you can see essentially that they reflect the object that they are captured here. They reflect the lights in different ways. Okay, so this is the principle behind this light reflection. And for each different wavelengths, of course, the object in question will reflect the light differently. So we have here example of a fruit, for instance, which is given certain wavelengths, it reflects the color in a different way, or the example of wood, which also reflects the light in different ways. Why am I making this example? Because the specific application we are dealing with in this project are about wood recognition and in principle also fruits recognition. So what we can do with hyperspectral images? Well, hyperspectral images can be used pretty much as normal images for image classification task. But here the problem is now to understand how to do this classification, because we are dealing with much richer images. So in the state of the art, in the literature, typically this classification step is carried out following two phases. On the first phase, the feature of the images are manually extracted. So we want to identify, for instance, which spectral bands are more important or more representative for specific features. And once we extracted that, then we can use normal classifiers like supervector machine, linear regression, logistic regression, and so on, to classify the extracted features. This, of course, is a time-consuming process, because you have to, on the one hand, extract the feature and manually sometimes, and then apply another classifier. So what is the ideal scenario here is to reuse deep learning classification framework as a way to automatically extract features of these hyperspectral images and to use them to classify the images. This is the way in which we would like to use these deep learning frameworks in our project. So we can see as input of our framework for classification of spectral image, we pass an image, an hyperspectral image representing, for instance, in this case, a piece of wood board. And what we would like to have as a result is the wood board in which the different classes that we would like to detect are highlighted. Okay, so in this specific case, we are interested in the recognition of two kinds of parts of the wood, which is the hardwood and the sapwood, and these are essentially recognized by our framework. Or we might be interested also in detecting wood fungi in an automatic way, so a specific kind of fungi that affect the wood, and but the principle behind it remains the same. So to use this framework to automatically identify this disease of the fungus. And the way in which we aim to do that, well, is by means of this framework, which we call an end-to-end framework for hyperspectral image classification, in which, as you can see, as input, we provide an hyperspectral image with a certain number of bands. Then we process, on the one hand, the spatial information of the image, and on the other hand, we process the spectral information of the image, in which we try to come up with a classification score for each of these branches, and then eventually we like to merge those results for finally having as output of the framework a segmentation map, a classification map, which, as we saw in the previous slides, is able to highlight different classes in our wood board. So the main idea behind this framework is not to reinvent the wheel of the deep learning framework, but to reuse as much as possible existing technologies. And this is achieved essentially adapting existing network, which are used to classify RGB images. So they need to be, this network, they need to be adapted, they need to adapted to deal with hyperspectral data. And the way in which this adaptation is carried out is essentially by means of two phases, or two steps. So on the first step, we adapt the structure of the network. So to adapt it to accept more bands, for instance, or to adapt to the output that we are dealing with. So if a pre-trained network, for instance, is usually able to classify 1,000 classes, and we are not interested in 2 classes, like in our case, then we need to modify the output of this network. So this is the first adaptation that we need to carry out. The second adaptation that we need to carry out is, once this structure has been defined, to fine-tune the network. So we don't want to retrain the network from scratch, because we know that it's a very time-consuming task, and we might want to reuse as much as possible of the pre-trained network that were already trained on different data sets. And this process, this step is called fine-tuning or transfer learning, and this is a process according to which you are able to adapt the learned parameter of your network to your specific problem. Now I'm going to leave the word to Bojan, who will explain a bit more in details the spatial and spectral classifier in relation to the hyperspectral image classification task. Thanks.
Hi, So I will briefly introduce the spatial and spectrum classifier in details. So for the data set we used is that provided by MikroTik. Okay.
Well, we see.
Yeah.
Okay, now it's working.
Okay.
Yeah, go ahead.
So the data we have using is provided by MikroTik. The hyperspectral images of the old samples in total is 47 bands, 47 boards, and in a very large size. So for our experiment, we extracted the cuboid samples.
Sorry, sorry for interrupting you again. Could you turn off the video to save bandwidth so we see the slides?
The camera?
The camera, right.
Okay. Is that working?
Right now, we still don't see the slides.
I can see the slides.
Yeah. Stop this. Right now we see the slides. Okay, I think you can. No, now we see the video.
Okay.
Just screen sharing without the camera.
Okay, can you see the slides?
Let's wait a bit. All right. Now we see the slides. Okay.
Okay. Thanks. So for the experiment part, we extract the cuboid samples that for the training is 133 and 66 for the testing. And the cuboid size is 32 by 32 by 320. It's the total number of bands that's captured by the camera. So for the spatial classifier that we adopt the pre-trained network called CIFAR10net for processing the hyperspectral images. The main the modifications you can see is the changes the input layers and also the output layers. Since the CIFAR10net has only applied to the normal RGB images with 3 bands, but now we have much more. And also the output layers for CIFAR10, it's used for the 10 categories classification. And for us, we have only 2 categories. So for because this the spatial classifier, it's in process that it only generates just 1 label for 1 cuboid in size of 32 by 32. And since now we have a much larger size of the wood images, so basically, the spatial classifier block consists of 2 phases. In phase 1, that we do classification label by block. Then we have a low resolution classification mask. Then we do the upsampling part, try to map the low resolution classification map to higher resolution classification masks. You see in the right part. So then we were the input size and the output size from the spatial classifier block would be the same, and it will be used for the merging process in later. So for the spectrum classifier part, it's again we still adopt the same CIFAR10net for the spectral classifier, but you can see in the right that the processed images are much different from the original ones. And here, let's go to see convolutions in spatial domain. Here you can see it's one typical 4-band images with convolution kernels, with 4 convolution kernels. We can see that each kernel operates independently, just band by band, then extract the features, then combine them into 1 feature map. So, but in this way, that all the band information are get compressed just into 1, and the interrelationships between the bands are did not captured by the kernels. Since we are more focusing on this, since we are using this spectrum classifier, we want to have focus on the spectral bands. So we want to have a convolution in spectral domain. So here you can see that this is an example of the hyperspectral images has many bands. So what we want is to have a kernel directions moving in spectral bands, in spectral dimensions, so that to capture the interrelationships between the bands. Then we can have our classifier. So the first step we do like data shape transformations. So each extracted cubes will be transformed into a stack of vectors. Then we stack them together, become our data set. Then we feed into the modified CIVATEN classifier to do the trainings. Then we will have the classified label at the pixel level. So here is example output from the spectral classifiers. So what we have is the input. I have labeled this ground truth. The green part is the sapwood. The blue part is the heartwood. So what we will get from this spectral domain is the middle one and the right one. The red dots just is a label for the misclassified the pixels, and also you can see here that the input and the output will have the same size, so it will be in the final fusion part. These results will be fused with the results from the spatial parts. That's basically just a brief description about our end-to-end framework for generating the final classification map. So we, as we already introduced, that Roberto is the API for this project to me. I'm the assistant researcher for this project since 2020. And also we have a list group of members, collaborators. So yeah, thanks for their contributions. And if you want to know more, so please feel free to send us the emails or visit our project website. Thanks.
All right, thank you very much. We got a bit over time because it's the last speak, so we have time. Are there any questions from the audience? No questions? All right, so thank you again. And so we will stop this track here now because we are almost at 6 o'clock. So this was the software architect track. All the talks will be online on YouTube, so you can, in case someone will re-see something, they can just go to YouTube with the slides and the whole presentations. And we close here and see you tomorrow at 9 o'clock for continuing the SFSCon. Thank you for being here and have a good evening. Thank you.